Good day. I'm adjunct professor at Brock University. I started in the fall of 2020. Today, I wanted to speak for about the next 30-40 minutes on water and climate. So the focus of this talk is really showing the relationship between water and climate, speaking about in uncertain times and inconveniences. So I already introduced myself, but there's a little bit more detail about my particular background. I was a Brock graduate in 1975 in math and physics, and recently I've just retired from the Environment and Climate Change Canada and the president of the World Meteorological Organization, of which I spent the last decade plus in supporting both the international community as well as that in Canada. In terms of just a little background of Environment and Climate Change Canada, for those who aren't aware, it's really has five longstanding institutions. The Environment Department was created in 1971 with the emphasis on environmental protection, but it brought in the Canadian Wildlife Service, National Park Service, Water Survey of Canada, and Meteorological Service of Canada. Both those last two I was responsible for from as the Assistant Deputy Minister from 2006 to 2019. In terms of the World Meteorological Organization, this is a UN specialized agency. It also has a long history. It was originated in 1873. It officially joined the UN with its creation in 1951, but it's the authoritative voice on water, climate, and weather. And in particular, it speaks to the world about the state and change of weather and climate around the world. It also has a mission to support public safety, food production, prosperity, and safe transportation. It's kind of its origins for its beginnings. And it does its work through establishing effective policy frameworks that set standards for data and science, how information can be used in an interoperable way. It comprises almost every nation of the world as a member of the organization. So I'm going to speak on the challenges of sustainable management of water resources, in particular the consequences of a changing climate. I've outlined here 9 challenges, some of which you may be very familiar with in terms of, scarcity of water resources. I want to emphasize the behavioral dimension, which relates to this aspect that it's essential for life on the planet. And as a public, we tend to think about it as a public good. In many ways, we end up going to we go to a beach, we enjoy the lake, others can enjoy the lake. So it's in that a definition of a public good. But in reality, it is managed as a private good and through licensing and other arrangements. But it does kind of foster a behavior of undervaluing or underappreciating, this precious resource we have on our planet. There are issues related to overconsumption, and we just think that in many ways, you turn on the faucet and the water flows. You don't tend to think about what the reservoir may look like in terms of our own behavior. So there's a tendency already in the world for a lot of overconsumption, particularly in regions of the world or in Canada where we believe we have significant water resources. As a nation, we do. But in terms of drivers that are really influencing water supply, there are primarily 3 of them. They relate to the demographics. By 2050, we're going to have population growth that'd be close to 10 billion people. And we've also, in the same time period, there will be a, following current trends, a pattern of increased urbanization, mega cities and their growth, and as we collect in these locations, we tend to increase our demand and use of water resources. So while we have 7 billion that are using a finite set of resources, by the time we get to 10 billion, we're still using a finite set of resources to be distributed among more people. And we get to 2080, there's an expectation that will be another 2 to 3 billion people on this planet. So this introduces, you know, some increased pressures. Economic is another driver. We use water for a lot of things in terms of agriculture, food production, energy, resource extraction, etc. And there's an emphasis in the world to eradicate poverty. In doing so, we're actually strengthening or increasing the proportion of the world's population that are in a that I could say would be in the, say, the middle class. And this too will have an impact on how much water we need as a society. But finally, it's the this aspect of climate change and an eroding awareness of what are the state of our water resources. Climate change is going to alter the predictable supply of water resources and will have an impact on ecosystem services to which as a society we have a dependency. But there has been also this trend where the amount of infrastructure that actually monitors the state of our water resources has been in decline for the last 2 decades. So I'll speak more to these kind of challenges going forward. I like to show this as a baseline water stress of the major water basins in the world. And this is from the World Bank. It shows the area in red, of course, is where the water stress is the highest. And, you know, it's shouldn't be unfamiliar with you. We've heard about issues in the Middle East, southwestern North America, where, you know, we hear about these dry and drought-like conditions, and also in areas like Southeast Australia, where we have significant population, but at the same time, you know, the actual resources available to them are minimal, and on top of that, the amplification by climate change is going to increase that particular stress. Graphic about where the Earth's water is just a reminder of how precious water, freshwater resources are. Desalination of water, which is often you see in the Middle East, there's some of that in Australia, is very energy intensive and also very expensive as a to gain water that way. And as a consequence, of course, it's counterintuitive, where, you know, we're going to use a lot of energy resources in order to produce water. At the same time, we've got to think about energy switching in order to combat the implications of climate change. So there's kind of a paradox between those two things. But the reality is that water that's actually accessible for economic and human consumption is really only about 1% of the available fresh water, and most of that is located in 5 major countries of the world, Canada being one, China another, Brazil, etc. So in the graphic on the bottom corner, which is really showing that as of this graphic is, I think, in 2016, shows that around the world, the use of water, 2/3 of it supports agriculture. Developing countries, that's closer to 80 to 85%. You can see the proportion that is being allocated. And as we move to renewable energies, more and more demand will be using water resources as one of the means of supporting cleaner energy sources going forward. So the next one just talks a little bit about the aquifers, and this too is I think in around 2014. GRACE is a satellite that measures the gravitational force of the planet, and by doing so, when we have changes of snow and ice, for example, or change of the amount of water that may be held in a lake, changes the gravitational force, and as a consequence, we can measure the depletion. And so this is looking at aquifers, and it's looking at the fact that as they deplete, it changes the gravitational force, and it makes kind of a depiction of what we see around the world. And blue where we're showing recharge, and red is where we're showing depletion. And so in some parts of the world, we're seeing an example over, if you look at India, you can see in the Himalayas, we're showing depletion. Most of that is in glaciers. And I'll speak to this a little bit later, but there's about 3.5 billion people in Asia that depend on water that comes from snow and ice, glacier-fed water systems that go into these rivers that are supporting the needs of almost half the population of the world, about 40%. And that is actually very significant in the context that at the current rate of change, the further depletion of snow and ice in these regions are going to have some downstream consequences for water scarcity and drought, and will have an impact, of course, on the economy. I like this phrase that you can't manage what you don't measure. If you recall, I mentioned earlier that one of the things that we've noticed the most is that in the measurement of water resources. But another point, which I didn't really stress on that first slide, had to do with the transboundary nature of water. About half of the planet's land surface has transboundary water systems. This graphic that I've shown on the right-hand side is really just showing 148 countries, including territories, that have at least one transboundary river basin. So in Canada, for instance, we have all along the border, for the most part, we have rivers that flow north or south, and they have, and these are shared with the United States. Milk River being one example, led to the 1908 treaty between Canada and the United States on sharing water resources, which is a key role that the Water Survey of Canada plays, managing water resources to ensure that the resource is properly shared between Canada and the United States. So this applies in many places, the Nile River, the Amazon, etc. These major river basins of the world all basically are transboundary in nature, and some have a few countries, some have as much as 10 countries. It relies on monitoring, understanding the water resource, what is actually available in the basin and how it can be shared. It talks about governance as being important, transparency. These are important principles to kind of avoid civil instability and conflict. And so this is a very important aspect, and this is what led to the Water Convention that was first signed by the European Commission on Economic Development, and so that's ECE, and that has become a UN body now in which other river basins in the world are sort of ratifying that agreement about having a integrated water resource management. So I'm going to move on a little bit to talk about the science, because it's really important in climate change to understand what the basis for how the risks are being amplified and the strength of the science. And I'm going to start by saying that the first, I think, significant phase in in climate science happened with this onset of a coordinated effort of in exchange of Earth observation information amongst nations. So the World Meteorological Organization is the body that is in place that distributes most of atmospheric data, and now in relation with the UNESCO, which is a science, the science body in the UN, are doing this for ocean data as well. The distributing this information in real time, and it uses multiple platforms. So take advantage of aircraft that fly, it's ships at sea. We have Argo floats. These are basically submersible instruments that go into the ocean and measure ocean currents and ocean the temperature profiles of the ocean and the salinity and even the geochemical analysis of the ocean, how much carbon is in the ocean, etc. These are things that have kind of evolved, and this kind of started in earnest with the onset of satellites, which started in the 1960s, and today we have more than 450 Earth observing environmental satellites that are looking at different aspects of the environment, whether they're measuring sea level, whether they're measuring gravitational force, whether they're measuring sea surface temperature, whether they're measuring the radiance of the Earth's surface, how it's changing, whether the moisture profiles in the atmosphere, and even measuring carbon in equivalent carbon dioxide and methane releases, etc. This is generating tens of terabytes of data daily. And that's a whole lot of information. And I'm going to speak to in a minute how that information has, how we found ways of kind of bringing this information together. But more importantly, this also has provided the foundation for a lot of the climate research that put in place. Under the World Climate Research Program, which started in 1984, they had taken the world scientists and organized them to do more coordinated research in trying to understand the climate system, its forcings, the if the aim of understanding, for instance, how ice sheets collapse, how the ocean currents are changing, or how the large-scale circulations, for instance, the Atlantic deep water circulation works. All of these major forces that influence the Earth's climate system, better understand those. And that has led to our ability to create models, numerical models, that kind of integrate this information together. So this also has created a huge body of science around climate that has filled tomes and tomes of information. And from the process of starting in the 80s up till now, our knowledge of the climate system has significantly advanced. And there have been hundreds of thousands of scientists that have worked on this focus, and we have established in the first World Climate Conference in 1979 the need to establish a science assessment body, which was the Intergovernmental Panel on Climate Change, and they have been producing assessment reports. The first one at the Rio Conference in 1992, and the last one in support of the Paris meeting in 2015. This science body has helped understand changes in the climate system, understand better what the impacts of inaction would represent, and also the implications kind of going forward as we project change over future. So the performance of weather and climate models is going to be improved. And I like to show this only to illustrate that weather forecast models, and it's often confused, and some of the naysayers about climate say, well, you can't get a weather forecast right in 2 weeks. How can we be confident about a climate model? The reality is these techniques are quite different. Weather forecasts require taking the initial state as we see it today and then moving that forward through dynamic processes, understanding, physics and how water gets distributed and everything else. And we use tens of terabytes of data that has gone into this to help improve that. In climate, it's a different process. We actually create a model of the current climate system, and we perturbate that by changing aerosol content or changing the level of carbon dioxide. And so why we can project over time changes in the climate system, or we call that climate change, is because we amplify, if we said the current rate of emissions in the atmosphere is extended without any abatement, this will, over the next 50 years, create a different kind of climate. And a different situation, if we did have abatement or we did sort of tackle zero net emissions, say by 2050, then we would say you would have to start flattening the curve, to use the COVID phrase, flattening the curve on the carbon emissions, starting now, and then we see what does that look like. And so then we do a schematic of how does the emission profile change over time, and that's then fed into these models, and that's why we can show how these differences are there. So weather modeling and climate modeling are different, but they use tens of terabytes of data that go into them in order to validate that. The reality is climate prediction has improved primarily from the convergence of all this Earth system science that's been done, this high performance computing technologies, and this kind of data science and artificial intelligence have all kind of come together. That's allowed us to have a lot more confidence. There's about 40 of these models, global models, run around the world, a little bit more now. And we use these as an ensemble. In other words, we bring them all together and we say that, what are all these models saying? They're all sort of slightly different foundations, but they do tell us something about persistent trends. And based on this, and we do these intercomparisons between all these model outputs in order to help us with some of the impact studies. And it gives us a lot more confidence when all of them are kind of indicating the same things. And it says that, where one model may have some certain weaknesses in how it may physically represent something in the climate system, another model might be better at it. If they're both showing the same kind of outcomes, it gives the community confidence that these changes are actually are more certain. And climate models, well, they may have been atmospheric in their early days. Today, as you can see from this graphic on the screen, they're much more. They integrate the land, the ocean, the ice, even we've got today. We're starting to integrate snow and ice over land, particulates, better understanding of the carbon cycle, that the characterization of vegetation and its behavior, how it changes, how it becomes adjusted over time, where you may have dieback of, say, tropical forests in the Amazon and dieback of the boreal forest as a consequence of increased pressure on the planet in terms of the types of changes you would expect to see in precipitation regimes at So the evidence is pretty unequivocal in that the planet is warming and climate is changing. And the IPCC reports have highlighted the fact that the human influence is is there, and we measure the vital signs of change through a number of parameters, and that includes global temperatures and water vapor and sea ice, change of scale of sea ice, the ocean heat content. Where does how's the carbon cycles, etc. So we have these kind of broad indicators that tell us something about what is changing and how rapid is that change taking place, and is it consistent with what we're seeing in sort of how we model the model going forward, the climate system. And there is good accord between what we see and what we project. We also see that because we have these tools now, a climate model, you can actually take certain features out, such as the carbon cycle, and say, well, what happens if there is no carbon dioxide? What will happen to the climate system based on current trends and shifts? You can see that a world without the anthropogenic interference in the world with, and it's quite different in its behavior. And IPCC used this in order to share their results with decision makers, and I'll come up with to that shortly. So what happened in 2020? Here's a picture of the planet. This shows the temperature anomaly between 1981 and 2010. They chose that reference point just to highlight what the last 10 years looks like. So this is what would be kind of over a 30-year, a 40-year average, a 30-year average. Then they look at what does 2020 look like, and you can see it pronounced red is warmer, blue is cooler. And when you, there's a couple of features I want to highlight here. The first is you can see that the Arctic region is warming at almost 4 times the rate of the warming of the planet. And this is alarming because we have ice sheets in Greenland in particular, and I'll speak to that shortly, where we see the significant decline in the loss of ice mass for Greenland is almost twice the rate of Antarctica. But you do see in Antarctica, also some warming, and this has the scientists concerned. If I had shown you a picture of 2016, you would have seen as a pronounced warming over Alaska and northern Canada and in the western side. And this had to do with the fact that we had an El Nino in 2016, which has a way of amplifying the heat content in the atmosphere. We had in 2020 an El Nino, which is the La Nina, which is the opposite of an El Nino. And in a sense, that little blue spot you see off of the coast of South America is the cooling of the Pacific Ocean. And this anomaly switches between a warming and a cooling. Has about a 7-year cycle, but the intensity of these cycles are being seen and measured as a consequence of the change of ocean heat and content. We're seeing this much more profound, but it's not changing, and that's the key point. The fact that we had a La Nina cycle, we still had the highest, the warmest temperature on record, tied with 2016 for 2020. The two charts on the right just show the trend from 1880 to now, and you can see that it's basically going up, and these charts you've probably seen before. But the chart below is separating the shift between what we see in a sort of integrated land-ocean, which is how we measure the change of the global temperature of the planet, which is the green line. On the line on the top is the heating over land. And this is a bit concerning because some of the consequences of climate change are already being felt, and in part because the land is heating much faster than the ocean. Essentially, that's what that's showing. And it's over 1.5 degrees temperature difference over the pre-industrial period. So climate change is striking harder and more rapidly than expected, and you can see that we currently have the rate at about 415 parts per million. So even with a slight downturn in CO2 emissions that we've measured, and we do this through reference stations in about 26 of them around the world, where we measure carbon dioxide to a standard. What we've seen, we saw this little downturn in 2008 with the global recession, but there's nothing institutionally put in place that's actually going to maintain that reduction. What we're actually going to see is, as soon as the economy starts picking up after the COVID pandemic, we'll likely just go back on track to continue to see record highs. It was a 62% increase between 1990 and 2019. And, you know, the consequences is that this year there have been pronounced heat waves. For instance, you might recall around 2008 or 2009, we had significant loss of life in Europe. France, for instance, lost 15,000 plus people as to essentially heat exhaustion, exposure. And that also happened in Russia. And we had heat waves in, for instance, this year also had significant impact on millions of people, actually. California had 13 successive heat waves. That was a record for them. They've never been where they have this kind of duration of heat. Also contributes to the fact that it's about 30 to 50% more likely, as a consequence of climate change, that we'll have wildfires that are more intense and last longer. This is a case in California. It was a record fire season. You recall a few years ago, record fire season in Western Canada. So the indicators are there, and this climate change is shifting our patterns. And so this is looking at, you know, at 2030. This was done after the IPCC publications that came out in 2015. So this work is the Global Environment Facility, which is part of the United Nations Development Program, where they kind of do a census of the environment, and they publish this about every 5 years. And this was their census about the climate change influence on climate, on shifting precipitation patterns, and more importantly, its particular impact on how it's going to change the risk profile on water stress. And you can see it's unusual that they didn't include Australia here. I can't explain why that's not there, but it actually, based on my knowledge and of what's going on in that part of the world, it would show some red, particularly on the southeast side, where most of the population of Australia live. You can see that the zones are going to be in northern Africa, just in the southern edge of the Sahara. They're going to have significant stresses in the Congo and out to Senegal and that kind of in that region. But below, there's an expectation that in the central part of Africa, that they could have increased water resources to support crop production. So there's some opportunities as well as pressures in this process. And I've already highlighted the areas of the change in the cryosphere, particularly in mountains and water-fed systems. In Africa, Mount Kilimanjaro, for instance, is a significant source of water resources for Africa, particularly for that sort of northern belt of Africa, south of the Sahara, and this is essentially having huge impact in terms of decline. This is just a graphic that shows change, and this one's actually from the Himalayas to where the glaciers are basically dried up. The two charts on the right-hand side, one is for showing the ice loss for the Greenland ice sheets, and Antarctica is the one on the bottom. And you can see the rate of change from just 2004 to 2019 in the degree of ice loss. So isn't just about projecting to the future. The current reality is putting us under significant stress. So in Paris, there was a big discussion about 1.5 versus 2 degrees. 2 degrees came out of a conference that was held in Bergen, Norway. It was in the late 1980s. It was focused on trying to define what is dangerous interference with the climate system. And at that time, they felt 2 degrees was a reasonable representation based on what they knew then. In the Paris discussion, particularly for small island developing states, are concerned that 2 degrees might actually result in some of those nations no longer existing, being underwater. And there was also a lot of studies of the cryosphere that had just kind of come out after the cutoff date of the science for supporting the IPCC report that supported the Paris meeting. And so they did a special report that came out a couple of years ago, and I just wanted to kind of highlight the differences in the context of water. The first is availability of water resources. That, in a 1.5 degree world versus a 2 degree world, 50% more people would experience water stress. If we kept it to 1.5, it'd be 50% of that population less. Heat stress. 400 million more people would be exposed to extreme heat waves in a 2 degree world versus a 1.5 degree world. Drought, 60 million more people exposed to extreme drought in a 2 degree world. And extreme precipitation increase, especially in the northern hemisphere, higher latitudes, some mountain regions, more rain, less snow, and Southeast Asia. In many developing countries, they lack the built infrastructure for water retention, and particularly in regions that had depended on snowpack to provide their water resources for the year, they never had seen the need for this. So for adaptation, they have to start to think about how they're going to manage water. And by damming or building water reservoirs, these sort of amplify the transboundary water issues, which I've already highlighted. So there's no easy answer to how we're going to manage this kind of going forward. And the accelerated loss of ice and snow, of course, is estimated in a 2 degree world versus 1 degree, another 650 gigatons per year in polar and high mountain regions. So the consequence is significant. Finding a way to stay within 1.5 degrees is going to be more tolerable than 2. So how does the politicians or the government leaders then take all this information and how do they relate to it? Well, there's a body of the World Economic Forum in Davos. They do a polling, a survey of what are the world leaders thinking, what are the aspects that that they see as implicating their development. They have experts, panel of experts, both from economic and from a science point of view, and how these factors are kind of influencing what they call the global risk landscape. And they map that by impact. So the top right-hand quadrant is where the impact is highest, and the likelihood of it actually occurring, it's also the highest in that same quadrant. And the green dots on this chart tell you that these are the environmental factors, and they relate to natural disasters, biodiversity loss, extreme weather events, failure of taking appropriate carbon actions. They also look, in the red dots are looking at the societal factors that are influencing this. Could be social instability, uprising in countries, etc. But here they've kind of highlighted areas such as the likelihood that we'll have breakdown of governments or involuntary migration, etc. So they've tried to map these factors. Just to highlight a couple of key points on the environmental factors and the consequence they have. The top graphic on the left-hand side is comparing the decade from 1980 to 2000 with the decade from 2000 to 2020. Doesn't include 2020 data, it's only up to 2019. But it shows, if you look at the economic losses, it's about twice the consequence, about 3 trillion versus 1.6. And this has a lot of repercussions, particularly in developing countries where their economic systems are somewhat fragile anyway. And to be able to withstand or be resilient to these kind of impacts are difficult. You can also see on the very left-hand side the number of disasters that have been reported in these two 20-year periods have almost doubled as well. So things are heating up, so to speak. The number of people losing their life as a consequence of disasters has stayed relatively the same. The bottom graph really shows from about 1980 through to 2020 what has been the change of the distribution between the meteorological ones, so these would be like storms or hurricanes or cyclones and that kind of stuff, which is the green. The blue is the hydrological ones, and the orange are the climate risks. So these would be like droughts, etc., and the hydrological ones would be like floods. And you can see that the domination has been in the hydrological events, floods being most costly, and also these droughts and wildfires and other related factors that are in these climate-related ones are increasing, although not as significant, let's say, as these droughts and wildfires. They do have significant economic consequences. And my last point about this, in terms of the risk and vulnerabilities, is that there is a very strong correlation between these environmental factors and the consequences for water security, food security, human health, human migration, and social instability, societal instability. And these are very important. An illustration is that a very long, pronounced drought in Syria led to a migration of people from rural, the countryside into Damascus. And part of the conflict in the Syrian crisis was precipitated by the fact that they couldn't grow food, they didn't have adequate water supply, and they had to go to a place where they felt they could could be nurtured, I guess. And as a consequence, they went into civil war, and then we had millions of Syrians that had to migrate as refugees, environmental refugees to some extent, to different parts of the world. So this is showing that kind of relationship, and as more and more of that may happen, particularly in small island states or in coastal areas where we have a sea level rise, this kind of migration is going to become more of an important consideration. So in terms of, I show this in terms of food security or insecurity and climate change. This is a graph on the right-hand side, top right-hand side. It's looking at present day, where food stress is in terms of food insecurity by countries. And you can see that Africa's got significant issues, a lot of Southeast Asia, South America. And then there's other two. So the one below it is showing a case where measures are implemented to reduce greenhouse gases. On the one on the left is showing where there are no measures to reduce greenhouse gases. So it's and you can see without taking action, the risks to food security actually is amplified significantly in these regions. And these are very highly populated parts. Just look at India's almost completely red, and China is heading in the same direction. And there you have a significant population base of the world. And there's also, in terms of uneven economic impacts of climate change, going from a 1 degree, where we currently are, another 1 degree to 2 degree global temperature over pre-industrial has an impact on the per capita output. And what is striking about this is that the whole southern hemisphere, for the most part, is going to be implicated significantly in sort of an economic downturn. And this is where a lot of the development is, Southeast Asia as well, Indonesia, that kind of thing. And the countries that have a bit more resilience in allowing technology and evolution, economic evolution to take place, have found ways of compensating for that. So this is where you don't see particular change in Europe. You see that in Canada, there's actually an opportunity to become, to increase as a consequence of climate change. So there are positive benefits for the economy as well. And this was according to the International Monetary Fund on World Economic Outlook. So political response, I'm almost finished. These, I've talked about these. I mean, I represented Canada at the disaster risk reduction in Sendai, which was looking at creating a framework for risk management. The two aspects which were the weakest were the preparedness function and the recovery function. In the preparedness function, the early warning systems and the need to have in place, capacity to be more resilient to change. In the recovery side, how to sort of build back better. It's a sort of a logo that has come out of Sendai of how to build structures so that, it's like the Three Little Pigs story. You can continue to build your house of straw, but a big wind will still blow it down. If you build it out of brick, it's less likely to be blown down. So in areas where there are high risk of disasters, how do you build built infrastructure in a more resilient way? So essentially early warning, preparedness, and building codes. And even in Canada, even 5 years ago, we didn't have climate change built into our building codes. They were just based on what the last 30 years looked like. And the one thing you've learned from climate change is that, or the current climate system is, looking back over the last 30 to 50 years is no indicator of what the next 30 or 50 years would look like. So this idea of building climate change forcing or the factors that would amplify consequences of disasters would be built into building codes. Paris Agreement, as I've already mentioned, I was there in my capacity as president of the World Meteorological Organization, as part of the UN family. In that particular emphasis, I've already highlighted the importance of the 1.5 versus 2 degrees. It's a very fragile arrangement, and it depends on governments. In some respects, it's not legally binding in that the Kyoto framework established targets from the framework, from the agreement. Paris is where governments would do stock taking. There would be a stock taking process, and then governments would declare what their intentions are for reducing greenhouse gases. And based on those intentions, those would be legally binding in the context of compensation for damage and losses to other parts of the world. So it's a very complex agreement, but at the same time, striving for staying within a 2-degree world with ambition to keep it at 1.5. And the final thing, the Sustainable Development Goals, also agreed to in 2015. They set an agenda for 2030 with specific actions. It has 3 components to these goals. First one deals with the environmental goals, which is trying to give back to the environment. Then there's some social goals, such as eliminating poverty, and then there are economic goals about building better collaboration between private and public sectors, partnership engagements to produce better outcomes for all of humanity. And then the Water Convention was signed in 2016, and its focus is on dealing with the conflict, the transboundary nature of water and how that could be best managed, but has a very strong principle of integrated water resource management to be done for the basin at large and not by necessarily a territory that lies within a country. And so this is an extremely important arrangement going forward to deal with the water challenges. So I wanted to show this depiction. This is the Sustainable Development Goals, but it shows them all on the outside. And water, as influences them all, strongly relates to 5 of them. That's the darkest colors, like life on land, life below water, like marine life, good health and well-being, sanitation, and sustainable cities, where water will play a crucial role. But it supports, to a lesser degree, affordable and clean energy, zero hunger, no poverty, peace, justice, and strong institutions, climate action, etc. So these are important to understand how central water is to these broader agreements that have been put in place, and underscores, and all these agreements underscores the importance of measuring, monitoring the changing state of the environment in some cases, but water resources in particular. And so the UN has started with this kind of coordinated strategic water ambitions, they call them, and their emphasis is trying to improve the understanding of water, and this is primarily focused on water resources. So how to improve the understanding, and they've laid out kind of 4 critical ambitions that could kind of move a coalition of interests forward. And they've established this water coalition, which I'll speak to in a moment. And it looks at things such as building a comprehensive knowledge of the water resources, being able to monitor that, in near real time. What is that changing state, in order to provide early warning to support decision making, but also early warning so that they can be more resilient to floods and droughts and take, appropriate actions. And then improve policy development and decision making, or looking at how, the foundational information is actually used in the policy and decision making process, and the value, in a sense, underscoring the value of their commitment to continue to support the science foundations that inform evidence-based policy. And finally, improved water quality. Particularly, this is focused on Sustainable Goal 6, which is clean and sanitation and clean water. And they're looking at what are kind of core actions, and how do these actions then translate into the developing world, where many of the health problems are related to poor drinking water. So there's an important coalition in the UN now. It's being established with many UN agencies, but there's also civil society, private sector, and non-government organizations that are kind of forming this kind of coalition so that there can be coordinated action going forward. And so clear, from a point of view of conditions of success, the graphic is a matter of survival. In a sense, they talk about it from the context of water crisis, matter of survival. This was a report done in 2016 through the UN Water that looked at, was a high level. It had heads of state, 16 of them that developed this path forward in dealing with water and peace going forward, and outlined in there some critical conditions of success, and importantly, that the capacity needs of the developing world are realized. So my talk, I kind of captured it in about 10 themes. I'll leave this for you, as you can kind of read through them. But, these are kind of the key messages that came out of my talk. So thanks very much for listening to me today. I hope that the information I provided is interesting and provides you with better insight into the water resources challenges and how climate change is amplifying them as we go forward. So thank you.